evening. I hope you guys are having a wonderful day. This is going to be the second podcast in Chapter 10, and we are going to talk about calorimetry, and you may or may not have done one of the labs already, but we are going to be using for a calorimeter in our class styrofoam cups, and they work actually very, very well. We could do a better job and make some covers, as you see in the picture down here, but for what we're doing in class, they actually give us pretty good percent air, and they work really well. So a calorimeter is an insulated device used to measure changes in temperature and heat. Now, we talk about the same thing for heat exchange when we talk about kilojoules and how it relates to a calorie, and that's what they do. All the calories that you see on food labels, they burn the food, they burn it, and they figure out the amount of temperature that's going up based on the amount of water, the mass that's there. So you can see the picture here. They have such thing as bomb calorimeters, so they can figure out the amount of energy that's given there when TNT or something like that goes off. So calorimetry is science that's used all across the world to try to figure out heat exchange, because it's not something you can measure directly. You have to do it indirectly. So, 1 second here. Okay, sorry, I had to pause that a little bit, so if there's a little break here, that is why. So now we're talking about the heat of formation. So how do we measure this? You are given a gold sheet and it has its heat of formations, and if you look at the top of it, you can see that the units that they all are, let's see, is in kilojoules per mole of substance. So 1 mole of substance, it's giving off a certain number of kilojoules or taking it in. So the amount of heat substance has at a given temperature and pressure. Remember, it can be endothermic or exothermic, and this is how you read it, the change in heat of formation. So delta for change, H for heat, F for formation, is in the formation of compounds. And the change in heat of formation for free elements is 0. So what this means is that elements that are on the periodic chart, they don't have a heat of formation because that's how they exist. However, we believe that happened. The periodic chart, the elements are there, and there is no heat of formation, it is 0. And then again, for diatomic gases, it's going to be 0, and you have a list of those. And the rest of them, you can look on your gold sheet for that. It is not anything that you're going to have to memorize. Now, it looks like a lot of steps on how to figure this out, but really, it's a pretty simple thing. So again, it's our change in heat of the reaction. And so we're going to write our balanced equation, can never get away from that. We're going to look up the heat of formation for each reactant and product on your gold sheet, multiply by those coefficients, so that's why it's really important that we balance the equation, add them all up, and we're going to subtract, and we have our units in kilojoules per mole. So let's try this out on a couple examples. So my first example here, you can see that I have a single replacement reaction, and if I take a look at my heat of formation sheet, even if you don't recognize that aluminum is on the periodic chart in the way that it is, it still says 0 on your gold sheet also. So I know that aluminum in its natural state is 0. I know that iron in its natural state is going to be 0. And then I can look at my gold sheet, and I'm going to see that when this iron 2 oxide was formed, it released, remember that negative sign means exothermic, it released 822.2 kilojoules of energy, and aluminum oxide released a lot more energy, 1,669.8 kilojoules per mole. So to go ahead and find my change in heat, I need to take my products minus my reactants. So I'm going to take this side, subtract my reactant side. So we're going to be reading backwards, okay? So my change in heat is going to be my products, and I have to multiply by the coefficients. And so I can see that my first one is just going to be 0, so I don't really need to worry about that. But then I have 1 mole, and I'm just going to write the mole there so you don't forget to do that. It's going to be 1 mole of my aluminum oxide, so times its heat of formation, which is 1669.8 kilojoules per mole. And that is that side, that's my product side. And I'm going to subtract my reactants. And my first reactant is going to be 0 again. Plus, I have 1 mole of iron, what do we got here? Iron 3 oxide, and it releases 822.22 kilojoules of energy. And if I'm very careful in calculating this out, I get a release of 847.6 kilojoules per mole of energy. Now, you have to be really careful about this, and you have to remember that we are subtracting here. And so this one's to the tenths, and this is also to the 10th place, and so that's why my answer is going to be to the 10ths. And the negative sign here tells me that this is going to be an exothermic reaction when this single replacement happens. That's it. All right, so let's try it one more time. You guys are going to see that this propane is on your gold sheet, and when it formed, it released 103.8 kilojoules per mole. You're going to see most things are exothermic in nature, and this released 393, sorry, I couldn't read my writing, 393.5 kilojoules per mole. And water in the gaseous state, you do have to be careful about some of the phases because you're going to see water in there in the liquid phase and the gaseous phase. So this is going to release 241.8 kilojoules per mole. So now I do have some coefficients on these that I have to make sure that I pay attention to. And again, remember that we are going to take the summation of this side, subtract the summation of my reactant side. So product minus reactant. So in this first one I have 3 moles times its heat of formation of carbon dioxide. Sorry, I'm at home on this bamboo pad and I still don't write very well on this. Plus the number of moles here, which is 4, and times its heat of formation. Subtract the reactants. So my reactant side for this first one, I just have 1 mole, and it released 103.8 kilojoules of energy, and the second one is 0. Again, go ahead and be very careful when you're calculating this, and I am releasing 2,043.9 kilojoules per mole of energy. And again, pay attention to the sign, and it gave it to me as negative, so that means I have another exothermic reaction. All right, that is it, you guys. That's homework number 2. You got 2 examples here, so I don't think I need to do one from the homework, so go ahead and give that a try. I think you'll find that it's pretty straightforward as long as I can write and balance an equation. Have a wonderful night, and I will see you soon.